think some things about work done. Work done by a force is given by F dot, sorry, let's call the work done as du. Then du is F dot dr. In other words, u is a scalar, it's a number, and in order to find that, you need to take the dot product of the force and the distance moved, or the displacement, whatever you like to call that. Okay, so here are simple examples to illustrate this. If the application of a force moves the block by a distance dr in the direction shown, so linear displacement, then the work done in going from 1 to 2 is F times R2, which is the final position minus the initial position. So this thing is dr. Okay, and the work done is positive because the application of the force moves the particle in the direction of the force. So F dot dr is positive. However, you may get a case where there's a force F which leads to the particle moving in the leftward direction. Okay, this happens when, for example, if you have things falling under gravity and you apply a force which is less than mg, then you will have a case where this is true. So the work done by the force is F dot, well, I'll remove the dot because there's no real meaning to dot when it's a scalar. So F times R2 minus R1 is going to be negative. Okay, it's negative because F is opposite direction to dr. Okay, here is, yeah. It's a displacement. Displacement, typically we like to say it's the final position minus the initial position. So R2 is the final position, R1 is the initial position.
So if we have a crazy pattern, just like the shape of the nest, we just draw straight into it.
No, so if it's a crazy line, then you need to do F dot, so du is F dot dr. So if it's a crazy path, then you need to do F dot dr from 1 to 2. So you have to find F, put in that equation and integrate it from 1 to 2. So it's not going to be a straight line. The work done in moving a particle in this way, that way, could be different. So for gravity, you'll see that it's actually the same because the force is constant. If the force is a function of r, then yeah. But good question. So in general, I would recommend always using this formula to find the work done. Not just don't do F R2 minus R1. It's only true if F is a constant. Constant. Okay, the final thing is work done by normal force, right? A normal force acts because this block is placed on say a table. Work done by N. So what's the work done due to N? So dr is to the right or left, doesn't matter. N is at right angles to dr. So the dot product is going to give you its cosine. This is same as N times dr cosine of theta, where theta is angle between N and dr, right? That's the definition of dot product. So this is going to be 0. Clearly, N doesn't do any work in moving the block to the left or right. Okay, so before we start solving problems, I'll give a few. I'll show you formulas for work done due to gravity, due to spring force, and due to friction. And then I'll write the principle of work and energy, and we'll use those principles, well, that principle to solve problems today. So this is a quick recap of concepts to be used a bit later. Work done by gravity. So a particle is, assume it's moving, well, the force due to gravity acts downwards. Our convention is upwards is positive. So the work done is going to be mg y2 minus y1. Okay. So we know what the work done is, right? Force times displacement, but the way you'll use this convention, the sign convention is negative if so u12 is negative if dy is upwards and u12 is positive if dy is okay. And the simple reason is because mg acts downwards. If the displacement is downwards, the force times displacement is going to be positive because it's moving the mass downwards. If, however, force is applied downwards but the mass is moving upwards, then they are in opposite directions, which means you need to take the negative sign. Work done by spring. Okay, a spring is stretched or compressed. Let's take the case when it's stretched. Fs is the spring force, and the work done by the spring force is Fs ds from 1 to 2. Okay, so how do you, well, let me just show you how to do this dot product. Fs is, assuming that this is I, this is J, then the force due to the spring. So when you stretch the spring always wants to spring back to its original length. So Fs is going to be in the direction I've shown that, to the left. So Fs is along negative I and ds is along positive I. So the force due to a spring is K times S. Well, it's K times S minus S0, where S0 is the free length. So I dot I is going to be 1, right? The dot product of I with itself is 1. 1 to 2, so it's going to be negative ts.
1, 2, is that just to say origin, right?
Yeah, you can, let me put S1, S2. S2, S1. It's not the origin. It can be,
I mean, like the beginning.
yeah, from wherever it is. So it's usually, if it's stretched from S0 to S2, say, then S1 would be S0. But I'm assuming that it's some length which need not be the free length. So when you take this integral, it turns out that S0 actually disappears from the.
Is K here a spring constant?
K is a spring constant. So when you take the integral of this term, you get u12 as minus half ks2 square minus s1 square. It turns out that no matter how you do this derivation, either you move to the right where the spring is extended, you do the integral, you get that. If you assume the opposite one, which is you compress the spring initially, so the force is going to be in the right hand side, you still get the same answer, because it turns out that the restoring force always acts in the direction which takes the spring back to its original length. So no matter how you stretch the spring, the work done is always negative. Okay, so given that, I'm going to write down the principle of work energy, and this is something which we'll use in order to solve problems today. Okay, the principle of work energy says that net work done by a force equals the change in kinetic energy. So the net work done is U12. So this could be a problem where there's spring force, there's gravitational force. For all those forces should come in there. You should write those down on the left hand side. So that's equal to half mv2 square minus half mv1 square. Okay, so we'll use the notation T to denote the kinetic energy. So it's T2 minus T1, where T is half mv square. So the other way to write this down is T1 equals T2 plus U12. So what that's saying is that the initial, if the particle has a certain kinetic energy, let's say half mv1 square, the action of a force would cause it to do work on the particle. Okay, change the kinetic energy of the particle. So the initial kinetic energy is equal to the work done by the force plus the final kinetic energy. So that makes sense, intuitive sense, right? So what we'll do today is we will solve problems essentially applying the principle of work energy, and where we compute U12 using the formulas I've given there. Again, recap, the work done due to spring force is always negative. The work done by the gravity depends on the direction in which the particle moves. Okay, so again, you do not have to write this on posters, but this is not disjoint from what we've done previously in the class. We've been always doing this. We've been drawing free body diagrams. The same thing applies for problems here in this chapter. We got to write equations of motion. Okay. What I recommend is you want to do this only if forces need to be computed, like for example reaction forces. However, if you do not need to find reaction forces, then you're typically asked to find velocities, then you want to rather use this equation. Note that in that equation, which I just highlighted right now, there is no acceleration made. There's only kinetic energy and work done due to force. So if you're asked to find forces and acceleration, you want to do step 2, but sometimes you're not asked those things. You're asked to find the velocity, in which case you want to do step 3. So this is really an option. And then finally, as needed, sometimes you're given the acceleration, you can find the velocities using 4, or you can also find the displacement using 4, 2, or 3. Okay. Sometimes you'll see that in your best interest you might have to do both 2 and 3. Sometimes you need to choose 2 or 3. Now it turns out that if you take the force equilibrium equation, Newton's laws, and you integrate it once, you'll actually end up deriving equation which I wrote down there at part 3. Okay, T1 plus U12 equals T2 actually is what you get if you integrate F equals ma. So it's not like it's a different thing, it's the same thing, just that it is written in a slightly different way. So here are briefly what I just said about using the sign convention. The sign convention is very important because if you do not have the right sign convention in the problem, your answers will be wrong. Okay, so let's try to apply this to some problems. So design considerations for the bumper B on the 5 mg train. Okay, so when it says 5 mg, it is 5, I think it's mega gram or something like that, which is 5 times 10 raised to 3 kilogram. Requires the use of a non-linear spring having a deflection characteristics shown in the figure. So the spring is not a linear spring. You can see it's actually quadratic. It's a non-linear spring. Select the proper value of k. So the k is an unknown. So that the maximum deflection of the spring is limited to 0.2 meters when the car traveling at 4 meters per second strikes the rigid stop. Neglect the mass of the car wheels. So I guess it's very, very hard to see this with this resolution, but now maybe you can more clear. Okay, so the spring is not shown, but apparently there's a spring here. Okay, so what is told is when this thing is about here, it's like moving to the right at 4 meters per second. Okay, so it barely makes contact with the stop. It's moving at 4 meters per second. Because there's a spring, the spring absorbs energy, right? At 4 meters per second, kinetic energy is converted to spring energy, and the train or the bogie comes to a stop in 0.2 meters. You want to find that k, which will get the bogie or the train to stop in 0.2 meters. So again, this is over here, but the spring is unspread. There's a spring over here. It's moving at 4 meters per second to the right. You're going to find the spring constant so that the energy is totally dissipated. So it comes to rest when the spring has compressed a distance of 0.2 meters. 0.2 meters. Okay, so what you notice here is that the reason why this problem you do not want to use F equals ma to solve is you're not told to find the acceleration anywhere. You're only told to find you're told to find spring constant given something. You're given some information about the velocity and some information about the distance moved. So velocity and distance moved, and so you do not need acceleration in this problem. So the best way to solve this is to use principle of work energy because there is no acceleration involved. 0.2 s square, no, it's ks square, k times 0.2 square, but that's not the right way of, well, that's the spring constant only when it begins to make contact. That changes linear, in a non-linear fashion. So I'm going to draw the free body diagram. Just follow the recipe I wrote down the previous page, FBD. So mgn and spring force. It's always a good idea to draw the free body diagram, even if it's not asked, because there's always some credit given to a free body diagram. So I'm going to skip F equals ma because I don't care about the acceleration. I'm not told to find the acceleration. So principle of work energy, which says that the initial kinetic energy is equal to the work done by all forces acting on the body plus the final kinetic energy. Okay, so the initial kinetic energy is half mv1 square, where we're given v1 is 4 meters per second. The only force, now we are only interested in the motion in the x direction, right? So we only need to consider the work done due to forces in the x direction. The only force in the x direction is Fs. Okay, times ds. And I need to integrate this from S1 to S2. Now, let me put so that's the magnitude. I need to put the sign, the right sign. So the spring force, because the spring is getting compressed, and the property of a spring is that it always wants to get spring back to its original length, the spring force is acting to the left, as I've shown in the Freebody diagram. The ds, the displacement, is to the right. So Fs is to the left, ds is to the right, because the trolley is moving to the right. So I need to put a negative sign because Fs is this way, left, and ds is this way. Okay, and then what's the final kinetic energy? T2. What's T2? Yeah, it's 0. So half mv2 square, but v2 is 0. It comes to a stop, right? So half mv square, m is 5. Is it 5,000? It's 5,000. 5,000 times velocity. It's moving at 4 meters per second. Initially, so this is at the time it makes contact, the displacement of the spring is 0. It eventually stretches to 0.2. So it goes from 0 to 0.2. Fs is the spring force. It's k times s square, and then this is ds. So this is Fs. So k is an unknown. So if I integrate this, I get ks cubed divided by 3. Then 0.2 is the upper limit and 0 is the lower limit. So solving gives us k equals 15 times 10 raised to 6. So what's the units on k? So we're given f is ks square. The units of f is Newton. The units of s is meter square. So the units of k should have units of Newton per meter square. This is for units. So this is Newton per meter square. So normally a spring constant for a linear spring, the force is kx. So the spring constant is Newton per meter. But in this case, it's a non-linear spring, and the spring constant, the unit of spring constant, has to be found by looking at the equation of the spring, which is F equals ks squared. So that's the answer.
So
Yeah.
just to be clear, the 0.2 isn't the same as L, right? L and L naught.
It is like L and L. L naught in this case is 0.
Then 0.2 is L.
0.2 is L. So this is how it is. Spring. Okay. Initially the spring, which is here, is L0, but that is 0. And then finally it is stretched. That's L, which is 0.2. Any questions on this? should be negative. Huh. Yeah, k is not negative. Hold on. One sec. I think I wrote something wrong earlier. That's, yeah, so my bad. So what I did was right here, you got to go back, and I got this wrong. It's T1. Yeah, I got this wrong. This is T2 equals T1 plus U12, right? That was wrong. And so I need to go back here. This is T2. This is T1. So this should be 0. This should be. So this comes out to be negative. Negative, and so k is positive. But thanks for catching me on that. Yeah, my bad. Any other questions? No, k is the same. Just that no, it won't change. It will be the same, just that when I move this, yeah, I'll move it right this way. So this becomes negative. That's all. The spring which we have over here. Okay, so the 8 kg block is moving with an initial speed of 5 meters per second if the coefficient of kinetic friction is 0.25. Determine the compression in the spring when the block momentarily comes to a stop. So this is probably more visual than the previous one, right? So this block is moving to the right with the speed shown. The spring is initially uncompressed, so the force in the spring is 0. Some point of time B comes in contact with the spring, right? Because of that, because it's moving with the speed to the right, it tends to compress the spring, and the spring applies the force, right? Because the spring after all. You're going to find the distance the block B comes to rest. So because it's moving with some speed and there's friction, it's obviously going to come to A with a speed which is less than 5 meters per second, right? Thereafter, it's going to be acted upon by not only the spring force, it's also going to be acted upon by friction force. And many people actually ignore that. We had given this problem last year, and many people got it wrong, in spite of me doing this problem in class. So so the key is to draw the free body diagram. Really, if you get that wrong, then it becomes hard to solve the problem. So, free body diagram. Okay, I'm going to draw two free body diagrams because this is a case when the forces change when block B is moving, when the spring is not in contact with B versus when the spring is in contact with B. So, free body diagram before B touches A. So normal force mg, and there is friction, right? And friction always opposes motion. So friction force is going to be Fs, is to the left. Fbt after B touches A. So in this case, There's going to be a friction force for sure. In addition, there's going to be a spring force. Okay, I think I'm going to call this, let me call the friction force as F, because I'm going to reserve Fs for the spring force. So Fs is the spring force. So the spring force, why is it to the left? Well, when the spring gets compressed, there's a tendency of the spring to spring back to its original length. The only way the spring can spring back to its original length is the force is applied to the left, and that's where the spring force Fs is to the left. Okay, so next question is, what is the equation we use? Now, in this case again, you're given the velocity of block B, right? And you're told to find the distance A comes to rest, right? So velocity and distance, there's no hint of acceleration, there's no hint of forces. So you do not have to use F equals ma. You could use F equals ma, no harm in doing that. You'll have to, however, integrate the equations to get velocity. So instead of doing that, instead of integrating, you just apply principle of work energy. So I'm going to use the principle of work energy. T2 is T1 plus U12. Now, there are a number of ways you can use this equation. One way you can use this is you analyze the motion in two steps. The first step is B moves from where it is right now. It covers the distance of 2 meters. Right? So you can use principle of work energy between B to A. Just before it comes into contact, use the first Freebody diagram. So you will solve for the velocity of B when it is at A, but the spring is unstretched. Then you can use the second Freebody diagram when the spring is now not only acted upon by the spring force, but also by friction force, and analyze the motion from the time when it is at A to the point where it compresses the spring. So you could do that in 2 steps. No harm in doing that. What I'm going to try to do is I'm going to apply this for the whole scenario. So I'm going to sort of combine the Freebody diagram. So I'm going to start at the current position and by 2. So 1 would be this current position and 2 would be the position where the spring is compressed. So I'm going to skip applying it 2 times, but there's no harm in applying it 2 times. In fact, you might want to do it that way. It's much more slower and cleaner and easier to understand. So I'm going to use it. So 1 is going to be current position and 2 is going to be spring is fully compressed. Okay, so the final kinetic energy, this is when the block comes to rest, is going to be 0. The initial kinetic energy is half mv1 square, where v1 is what, 5 meters per second, right? Okay, what I'm missing on now is the work done by the forces. Okay, as I said, I'm analyzing the whole thing as one complete system. So I need to find the work done due to the friction force F. Okay, so there are 3 things. I need to find the magnitude, well, 2 things, magnitude and direction. The work done by the friction force is F, which is I've written here. I'll sub in the value a little later. But what's the distance the friction force acts? Is it 2? So this is 2, and then the spring gets compressed by distance x. So what I claim is that the force of friction acts for distance 2 plus x, right? Because even when it is compressing the spring, friction is actually sort of slowing down the block. Okay. The other question I have is, what's the magnitude of the force? Sorry, the magnitude of the work done. F is acting to the left, right? And the block is moving to the right. So since F and the displacement are in opposite directions, we have a negative sign. So this is going to be to the left, and this is going to be to the right. And then finally, I need to write the work done by the spring force, which is nice. It's always negative. Doesn't matter how which direction it moves. It's going to be half x square. Sorry, half kx square. So kax square. Okay. F is mu kmg. It's 0.25 times 5 times 9.81. V1 is, I think, 5 meters per second. Ka is 200. Okay, so given all that, you sub in the values for all those things except x, which is an unknown. You get a quadratic equation, right? It's second order. So you got to know how to solve a quadratic equation, which is a prereq. Once you solve the quadratic equation, you get two roots. It turns out that one root will either be, it'll most likely be negative, which is an inconsistent root. So you'll ignore that. You'll only use the root which is positive. So I'm just going to finish this. Simplify. So give me like 30 seconds. I'll just write it down, let you go. Simplification gives me 100x square plus 19.62x minus 60.76 equals 0. If you solve this quadratic equation, you get two roots. You only choose the positive root. That root is 0.6875 meters. Leap. This is the positive root. So that is the answer. Okay, so that's it for today. You have an exam on Friday. The syllabus tells you what is covered in the exam. Tomorrow, that is Wednesday, and on Friday, we'll do a review. There's already some practice problems which are essentially similar to your short answer questions already posted. We've posted the answer keys, so you should be able to solve it and check your answers, but we've not posted the solution, that is, how do you actually go about solving it. I'll post that tomorrow night. I'll also post some long answer questions for you to practice on, and that will be through the mock. This is a mastery, sorry. Yeah. I can't hear you.
If we pass exam 2, do we have to go through it?
If you pass, no. If you pass the exam, you do not have to go for extension.